If I turn the handle clockwise, you'll notice the needle here on the milliamp meter is deflected to the left. If I rotate the handle anti-clockwise, the needle on the milliamp meter is now deflected to the right. Now as I'm rotating the handle, the armature coil here is rotating against the invisible magnetic field from this permanent magnet. And that's the reason why we call this model a permanent magnet generator. Now because the armature coil is rotating within the magnetic environment of the magnet, a voltage, an EMF, will be induced in the coil and electrons will start to flow. Now that's Faraday's law. You're converting mechanical energy into electrical energy. Now the EMF produced will be alternating because the coil is spinning. It's constantly changing its polarity as it rotates. For example, the current flowing as a result of the voltage producer is changing direction. Now that flow of electrons is AC alternating current. Now the split ring commutator will rectify the current flow into DC direct current. The milliamp meter here is simply providing a visual interpretation as to the direction of the flow of electrons in the circuit. Now if we replace this split ring commutator with slip rings and brushes, there would be no rectification of the current flow. We therefore refer to this model as a PMA, a permanent magnet alternator. Now in this simple model, I'm rotating the armature coil against an invisible magnetic field from this magnet. I could remove this magnet and replace it with a field coil. Now this field coil now needs a voltage applied to it, and that's going to make this coil into a magnet. What I can now do is I can vary the current going through the field coil, and that in turn could vary the output of the alternator or generator, depending on whether I have a split ring commutator or slip rings and brushes. Or conversely, as the engine driving this alternator RPM increases, the output would increase. Or as the RPM of the engine slowed down, the output of the generator or alternator would reduce. So what I could do, at high RPM, I would reduce the voltage going through the field coil, and at low RPM I would increase the voltage through the field coil. By doing this, I can keep the output of the generator alternator constant even though the RPM is varying. So the voltage regulator would be placed in series with the field coil. One thing to understand about this model and the way it's built is the armature coil is where the current is produced. So whether we have a permanent magnet here or we have a field coil here as shown, the current that's produced, the output of this generator is produced in this armature coil, which means the windings of the armature coil need to be very heavy, in which case it's going to take a lot of energy from the engine to drive that heavy armature coil. The field coil is many thousands of turns of wire which are very thin. It's lighter than the armature coil. So why not rotate the field coil and keep the armature coil stationary? Now this DC alternator is taken from a car, and you can see here we're rotating the field coil. So a drive belt connected to this pulley here is rotating the field coil, Now initially we'll take 12 volts from the battery, connect them to these brushes here which are sprung loaded. They will make contact with the rotating slip rings, and that voltage into this field coil which is rotating, it will become a powerful magnet. These bits of iron here simply provide more strength to the magnetic field. Now that magnet is now rotating against a stationary armature coil which is around the circumference of the alternator inside, and that is where the current is produced. So now we're rotating the lighter field coil, which takes a lot less energy than what it would do to rotate the armature coil, which is very heavy. And that's why they do it that way when we're designing an alternator in either a car or a small aircraft. So talking now about the output of this alternator. As the field coil rotates, an EMF is produced in the armature coil and we have an output. But if the RPM of the engine increased, the output of the alternator would also increase, which is not acceptable. So all we would have to do there now is, through a voltage regulator connected in series with the rotating field coil, we'll reduce the voltage going into the field coil, and as a result of that, the output voltage, which had increased, would now decrease back to normal levels. Conversely, if the RPM of the alternator decreased without a voltage regulator, the output of the alternator would also decrease. So all I do now is I would increase the voltage going into the field coil, making the field coil into a more powerful magnet, and thus increasing the output of the alternator back to normal levels. So if the engine RPM increases, voltage regulator will decrease field excitation. If the RPM decreases, voltage regulator will increase field excitation, and thus the output of the alternator is kept constant even though the RPM of the engine is increasing or decreasing.